Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discussing about the classification of polynuclear and the heteronuclear aromatic compound. And before we have discussed about the aromatic character and the Huckel's rule. The statement of that, it stated that fully conjugated, planar and the cyclic system which contains 4n plus 2 pi electron is known as Huckel's rule and possesses all the characteristic feature of above mentioned, where n is equal to number any whole number 0, 1, 2, 3 etc. according to that we shall see. And there are two types of aromatic compound. One we can call it polynuclear aromatic compound. Another one we can call it heteronuclear aromatic compound. An aromatic compound, so here in case of the polynuclear aromatic compound, or we can call it as a homo-polycyclic compound. Homo, the meaning of that homo, the ring which is made by same atom, generally here in this case carbon atom, and therefore we can call it as a polynuclear aromatic compound. Heteronuclear aromatic compound, the name itself suggests that hetero means different other than carbon atom, like oxygen, sulfur or nitrogen atoms are involved in a ring of formation and obeying Huckel's rule are generally termed as heteronuclear aromatic compound. So let us see, first one is a benzene polynuclear aromatic compound. Let us discuss little bit introduction regarding that naphthalene. Naphthalene is an example of fused ring aromatic compound. If you observe the structure of naphthalene carefully, you will find that the two benzene rings are fused together by sharing 2 electrons, and the resulting compound is formed is called as aromatic compound, and which shows the aromatic character, and that's why naphthalene it is included in a polynuclear aromatic compound. When two rings that share a pair of carbon atom are said to be fused, the simplest and most important of the fused ring hydrocarbon are naphthalene, which has a molecular formula C10H8, and anthracene, which has a molecular formula C14H10, and a phenanthrene, which also has a molecular formula C14H10, occurrence about that naphthalene. All these hydrocarbons are obtained from coal tar, naphthalene being the most abundant 5% of all constituent of coal tar. Coal tar is a further fractionized into light oil fraction, middle oil and heavy oil fraction. Naphthalene crystallizes out on cooling middle oil and heavy oil fraction. Pure naphthalene is obtained by distillation of crude naphthalene. The molecular formula of naphthalene is C10H8 and nomenclature of C on the blackboard, or look at blackboard, nomenclature of naphthalene derivatives. As you know that nomenclature means what? The systematic way of giving the name of the organic compound is known as nomenclature system. Two systems are generally employed or generally used while naming the organic compound. One is a common name system and another one is a IUPAC system. Common name system, some of the compounds the scientists had given name of those compounds according to their history. Some of them are known by their common names, but some of the compounds there is a difficulty in naming in some compounds. It is very difficult to remember common name of those complex compound, and therefore the organic, or what we can say, the scientists formulated one committee and given one system or provided the system that is known as a IUPAC. And full form of that IUPAC everybody knows, but let me tell once again the full form of IUPAC. I stand for International Union of Pure and Applied Chemistry. That is a full form of, and there are certain rules. By following that rules we can give the correct name of the organic compounds. Here itself it is for naphthalene. Naphthalene can be represented by three resonance forms: first, second and third. Let us see. I am showing the structure. You can observe these structures carefully. One, I am putting the double bond at these places. Now I am showing second structure. Now I am putting the double bonds in this way. Now once again I am representing the structure of benzene and putting the double bonds at this position. Now if you observe this structure carefully, what do you see? Let me number the structure. This is a structure number 1. This would be the structure number 2, and this would be the structure number 3. Can you observe some differences in those rings? I will label these rings It's a A ring. This would be the B ring. Say this would be the A ring. This would be the B ring. This would be the A ring. This would be the B ring. Observe these rings. Now, in the first case, the name generally the numbering system are used, and numbering system are like this: 1, 2, 3, 4, 5, 6, 7, 8, and those carbon atoms sharing those are common to both the rings. They are labeled as 9 and 10, which is represented in structure number first. Now, if you observe the second structure, there are two sides. This side is termed as alpha. On left hand side, this is also as identical. If you look at exactly para to that alpha, it is also alpha. This is also as a alpha. This would be the symmetrical molecule, and therefore there are two non-equivalent positions present in the naphthalene. So one I have shown here with the letter alpha. Now another, if you observe this position and this position, and this position, are these positions identical or different? Yes, all these positions are the different, and therefore the labeling, I am labeling that position would be beta. This would be as a beta. This would be a beta. This will be a beta. Look at here. So what the differences you would see in structure first and second? Here the ring A and B looks both are aromatic in nature, but if you see these ring A and ring B, here A, in case of A, alternative conjugated double bonds are present. One, double bond, single bond, double bond, single bond, double bond, single bond, single bond, double bond, single bond, double bond, means this double bond is common to both the ring, and therefore both rings are aromatic in nature. But if you observe this structure very closely, you will find A structure would be the aromatic in nature, but B ring, it doesn't seem aromatic in nature. That's the noticeable point or the differentiating point which makes the first structure and the second structure is differently, they are different structures. Same thing in case of here. Now here A ring is a non-aromatic, whereas B ring is aromatic. In structure second, A ring is aromatic and B ring is a non-aromatic. So that's the difference you can clearly observe in those structures. So generally, this is the compound, this is the structure which fulfill all the criteria of aromatic character. It obeys Huckel's rule. It states that statement we already discussed in our previous lecture. It states that fully conjugated planar cyclic system which contains 4n plus 2 pi electron is known as Huckel's rule, and this first structure fulfilling all those essential criteria, necessary criteria, and therefore it is belonging to the aromatic compound, which is also called as polynuclear aromatic compound, and these two compounds does not seem to be aromatic, and therefore even though there are the different structure but this is the most probable structure of that naphthalene. Or naphthalene can be represented by three resonance forms. These are the resonance form. As we know that resonance form is nothing but as a hypothetical forms, because the electron, pi electron are not localized, they are delocalized. Continuous oscillation is taking place, and therefore we cannot identify the single bond and double bond in aromatic compound, because there is a continuous oscillation taking place. The electrons are not localized on that particular position. The electron density sharing equally all the carbon atom, and therefore that different structure are known as resonance structures. And as we know that, or you should remember, as the resonating structure goes on increasing, the stability of that compound goes on increasing. So that you should remember one statement regarding that aromatic compound. So naphthalene can be represented by three resonance forms, first, second, third, which are represented on blackboard. You can clearly see. Out of these structure, first is the most important, as both the rings in it have aromatic character. Structure second and third have only one ring, which is aromatic. Naphthalene forms two monosubstituted alpha and beta products that are differentiated by prefix 1 or 2, 1 and 2, or alpha and beta. Important derivatives of naphthalene are, let us see that derivatives, some of the derivatives which I am showing over here, which I am going to represent it over here. Now let us see one of the structure which I have drawn here. One Br is here. Now I am showing another structure over here, so you can remember this is a structure where OH I am putting here. One more structure which I have shown over here, you can remember this is a structure where I am putting one, I am introducing one group at this position and one which is at this position. And now let's see here. How do you say this? Look at the bromine atom attached at one carbon atom, and therefore you can start the numbering from here. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Look at the bromine atom, at which position it is present. It is present at one position, so that you can call it as a 1-bromo naphthalene. 1-bromo naphthalene. 1-bromo naphthalene. That is the name of this derivative. 1-bromo naphthalene. 1-bromo naphthalene. This is the name of this compound. Now look at here. This is a or we can say at what position that bromine, this is alpha position, this would be the beta position. Therefore, we can also call it alpha bromo naphthalene. Alpha bromo naphthalene. Now look at here. In this case, this is 1, 2, 3, 4. Once again 5, 6, 7, 8, 9 and 10. Essentially, this is a carbon atom with sharing both the benzene ring, and that's why number is given to that carbon atom are 9 and 10. And now the hydroxy group which is present at 2 position, we can call it as a 2-naphthal. You can call it as a 2-naphthal. Or you can say it is a beta-naphthal. Beta-naphthal. OL indicates as a hydroxyl group, and therefore we can call it as a this. Now let us say here, you can start the numbering either this side or that side, doesn't matter. So let us see here 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Look at carefully. What do you observe? You would observe the nitro group. There are 2 nitro group. One is present at 1 position, another is present at 5 position, and therefore relative positions 1 and 5 are written like this, then dash. How many nitro groups, same substituents are there? Therefore you can call it as a di. 2 are there. What is that? Nitro. So nitro, and that is a naphthalene. So this is the what we can call it as a IUPAC name of this compound, 1,5-dinitronaphthalene. Now let us move on to some more example. Essentially we are discussing about the nomenclature of naphthalene derivatives. So let's see some other example over here. So one example which I have shown here, you can observe this structure carefully. One group which is present at this position SO3H, and one which is present at this position, that is amino. So in this particular case here, sulfonic acid, which is a most oxidizable compound, or we can say it is a main substituent, and therefore according to the IUPAC rule, the main substituent should get the lowest possible number, and therefore you can start the numbering from this side, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. And now see the substituent where they are present, one at 6 position. So we can call it as a 6 amino, this one, because at 6 position amino group is present, 6 amino, then 2 naphthalene, sulfonic acid, 2 naphthalene sulfonic acid. This is the name we can suggest or we can give to that compound. Let us see one more example over here. So here I am showing, I am representing the structure of naphthalene substituted naphthalene derivatives NH2, here NO2, and at this position also NO2. Now all the substituents present in the same aromatic compound. So now from where you can start the numbering? You can start the numbering from this side. That is the only way, only possible numbering system available in this particular example. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now look at one position what is present and what is present at 2 and 4 position. Here let us say at 2 and 4 position nitro groups are there, total 2. According to as IUPAC, the suffixes are using. If 2 are there, you can call it as a, if only singles are present, then we can call it as a mono. 2 are there, di, 3 tri, 4 tetra, and so on. So here 2 4, 2 comma 4 dash dinitro, here you can call it as a dinitro, 2 4 dinitro naphthylamine, 1 naphthylamine, that is a name of this compound. So these are the different compound we have seen here, how to give IUPAC name of that compound. Now switching over to the next point what we are going to discuss, that is the synthesis of naphthalene according to as a Haworth. Let us see that synthesis of naphthalene, because naphthalene is a polynuclear compound and therefore we are discussing about the synthesis of naphthalene. Let's say here synthesis of naphthalene, synthesis of naphthalene by Haworth process, synthesis of naphthalene, or you can describe, you can say Haworth synthesis of naphthalene. There are the different ways or the preparation of naphthalene by Haworth process. So how do naphthalene is prepared in the laboratory? Haworth has developed a synthesis of naphthalene starting from benzene using Friedel-Crafts acylation reaction as follows. What he did, how he synthesized the naphthalene in the laboratory. Haworth is the first scientist who discovered the method of synthesis of naphthalene. He took the starting material, one of them is a benzene, another one is a succinic anhydride, and this reaction carried out under Friedel-Crafts Lewis acid catalyst use, and according to as a Friedel-Crafts acylation reaction takes place, and after getting that reaction intermediate, it is further treated with Clemmensen reduction, and as we know that Clemmensen reduction known for the conversion of carbonyl group into as a hydrocarbon, and after reducing that, the acid which is present at one terminal, which is cyclized by using hydrogen fluoride, and when cyclization takes place, tetranone obtained. That tetranone once again he used Clemmensen reduction for the conversion of carbonyl group into a hydrocarbon. He got tetraline, and for bringing the aromaticity, he treated that intermediate or that product with selenium or palladium charcoal. He obtained the desired product, that is nothing but as a naphthalene. So now let us see the starting material he has taken. For that, the benzene, this will be treated with the compound which I am showing over here, the succinic anhydride, and this succinic anhydride under the Lewis acid catalyst, there would be a Friedel-Crafts acylation reaction took place, and the compound form, or what we can say the intermediate form, is this one, like the C double bond O and hydroxy is there. So this compound is known as alpha benzophenone, and when this compound further treated with ZnHg in presence of HCl, which is known as a Clemmensen reduction, this carbonyl group get converted into hydrocarbons. Let me draw the structure once again like this. Here you will get C double bond O H. Then what he used as a hydrogen fluoride for cyclization purpose. After the cyclization, what he got, the cyclization took place and he got the product, this one, that is a tetranone he got, and after that once again there will be a ZnAg in presence of HCl, which is Clemmensen reduction. Once again Clemmensen reduction, this carbonyl group get further converted into this one. So we got, this is a compound, that is a tetraline. The compound which got is a tetraline, and now this tetraline further treated with selenium or palladium in presence of charcoal, the resulting compound obtained would be heated. They have got, this is the structure here which I have shown, that is nothing but as a naphthalene. This is a structure of naphthalene. See, this is a very simplest synthesis which is given by Haworth the scientist, he prepared this synthesis starting with benzene. This is he used benzene as a starting material with succinic anhydride, very famous reaction, well known reaction, Friedel-Crafts acylation reaction takes place, and we get this kind of the intermediate. This intermediate in acidic medium, which is known as a Clemmensen reduction. After the Clemmensen reduction, we will get this type of the compound. Here, here you remember there is a hydroxy acid is there, and for cyclization purpose, hydrogen chloride is used to get tetranone, this type of the derivative. Once again further treated with Clemmensen reduction gives this type of the compound which is known as a tetraline. Tetraline treated with selenium or palladium charcoal, heated it, will get the aromatization, and the resulting compound is called as naphthalene. So in this way we have seen how naphthalenes are synthesized in the laboratory by very famous synthesis which is known as the Haworth synthesis of naphthalene. So in the next lecture, upcoming lecture, we will discuss about the reaction of naphthalene. So, still then, have a nice day. Thank you.